So, in the earlier video we have looked at the output queued system. We have estimated the waiting time at the output queue by taking two different components and analyzing it thoroughly. We ultimately figured out that when the size of the switch becomes infinite, the output queue will behave as if it is a Markovian arrival process and it is a deterministic departure, one packet going per time slot. There is only one server, this is because I am talking about every output port separately, and the buffer size is infinite. Okay. But if it is a finite size switches, then n minus 1 by n will also get multiplied in the delay. So, that actually kind of gives an understanding or insight into the output queued system. But remember, you have to operate the switch at n times the speed up factor, okay, n times speed up factor you have to use. So, in one slot when a packet will arrive at the input or one slot when packet will go out, in the same time period you will be able to transfer n packets from input to output port. So, switch is operating at n times the speed. So, now we will talk about when my value of k, the speed up factor is 1, it is not n, which actually means packets cannot pass through the input queue if there is a contention, only one of them will be able to go to the output port. So, what does actually I mean by this is, if there are for example a situation like this, I am taking a 4 by 4. Now remember, you have to understand now that k is equal to 1, the speed up factor is unity. So, one slot one packet comes, one slot only one packet can go from input to output, not multiple of them. So, if there is a buffer here, so important thing here, you do not require buffering here, you require buffering here. In the output queued system only output side buffering will be required. Okay. So, if there is a packet like this, there is a front packet. So, I have 1, 1, 1, all 4 of them want to go to the outgoing port 1. What will happen? Only one of them have to be selected and it will go out and will be transmitted. So, in the next time slot some new packet which will be jumping to the next thing and these packets will still remain there. Okay. And these are contending packets. Now, let us try to analyze this particular switch. So, first question is, what is the maximum possible throughput which I can get in this particular switch? What is the maximum possible throughput? So, when this is going to happen? This will happen when I am going to operate this switch in saturation. So, the control variable for this switch is the probability that a packet is going to arrive in it. Remember, your time is slotted, there are many slots, every slot a packet will come or may not come for an input. So, I define that packet is going to arrive in a time slot for an input, this probability is given by p. Okay. So, this p is the load on the line. As this p is increasing, I keep on increasing p, so my output packets which are going out will also start increasing. At some point I will not be able to increase it any further. In case of output queued system, when p will become 1, output will also tend to become 1. Okay. So, it does not saturate, output queued system does not saturate, you can operate the switch even with when the probability of arrival is going from 0 to 1. But here even before I actually look at the output utilization, and if I change my p from 0 to 1, after some value of p you will no more be able to go to 1. So, output will be having less number of packets per slot coming out and it will saturate, it should saturate after this, you can't do much. Now, the question is, what is this value, how to find it out for an input queued system. So, let us investigate this particular case. So, now important thing, I have to now draw a timing diagram which will clarify the whole issue. So, everything is happening in terms of time slots. The way actually I am assuming that in these just before this is the I minus first slot, this is the ith slot. The way it is actually operating, At the end of this slot, just before that time period ends, how many packets are there? I am only looking at the packets in the front of the queue. I am also assuming that the moment you transfer a packet to the outgoing thing, immediately there is a packet always available behind it which will come to the front. There will never ever be a case when a packet is pushed out from input to output and there is no packet available. Packet is always available, it will be coming back to the front of the queue. So, at any point of time you will never see the front of the queues in any of the inputs to be free, they will always be occupied, it will be happening immediately. But the way it will be happening is, this will be the arrivals, this is all these packets which will be coming from second position to the first position will be happening here. I call it EMI, sorry, this is mth slot, not I, and this is the, so I will actually use a marker for time with a yellow one, okay. And then what will happen is, the packets will now be allowed to move out of all contending packets. So, they will be going out, and at the end of it, then there will be some input slots which will be available, because the packets have moved out in this half part, okay. And then what will happen is, in the next time slots half part, the packets from second position will move to first position. So, switch is always in saturation. So, okay, this is what we call operating the switch in the saturation regime, and basically what I want is, what is going to be my number of packets per unit slot in the outgoing port. So, we have to define certain variables. So, I will define them like this. First of all, I will define a variable called BMI, okay, let me write it down here. So, what I am actually doing is, I am looking at the head of the queues, and this is happening just closer after the packets have been transmitted out, okay, here. So, the number of packets, so some slots will be vacant whose packets have moved out to the outgoing port. The arrival from second to 1, that movement has not happened. I will look at these packets which are backlogged for that outgoing port. So, for 1, so this and this for example is backlogged, for 2 this is the backlog, so I will sum these up, and that is what is going to happen. This is the end of the mth slot. How many packets are there which are still pending at the head of the queue for port number I, that is what it actually means. So, I will write it down, number of packets waiting at the head of the queue for output I, at the end of mth time slot. So, you have to understand in terms of this timing diagram. So, BMI is actually at this point is Bm minus 1, because this is m minus 1 slot, okay. So, AMI is the new arrivals, then departures, and this value will be now BMI. And of course, this will exclude, because packets are going out before you are estimating this. So, these packets which are moving out to the outgoing port are excluded. This excludes Now this is a kind of a convenient, for my own convenience I have assumed this assumption. Actually this happens simultaneously, but this actually makes it much more easily mathematically tractable thing, that within a time slot different events, the sequence of those how they are happening I have actually identified and demarcated. So now what is going to be AI? I also need to define this. So let me write it down here. These are number of new packets foreign destination I coming in the mth time slot. So for different destinations, different arrival, total number of arrivals which are moving from second position to the head of the queue will be sum of these over all possible i's actually. Okay. So number of new packets for destination I moving to the free head of the queue in the beginning of mth time slot. So that is what is AMI. Now once you have this, I can very well write that whatever is my BMI, this should be equal to maximum of 0, whatever was there before at the end of the m minus first slot, okay, plus there were new arrivals from second position to the first position in the to the head of the queues, minus 1 because for an output only one can go out, the maximum of 0 these two, that is what should be new value of BMI. Now this equation is very similar to what we had used in the output queues also, okay, that is a kind of a batch arrival. Okay, here also batch arrival, but coming to the output of the head of the queue, there it was a batch arrival going to the output queue. So I can very well write down, if this is the expression, I can actually use the same value, same method, same expression which I had used earlier. So kindly refer to the earlier video for this particular thing. So we will end up in getting B bar will be given by n minus 1 by n, okay, into p square by 2 1 minus p, okay. So that actually essentially will depend on this statistics. So we will find out what is going to be my statistics which has to be used here. So what is p and what is n, that we need to identify. And especially when n will go to infinity, you will only have this particular thing. So we have to also look into what is the probability that AMI is equal to k. Now I do not have a fixed number of input terminals where packets are coming in, they are all going out, and out of that only I will be going to an outgoing port. Here number of packets which are coming to the input to the head of the queue, that itself is changing, it is not n every time, okay, it is changing every time depending on how many free head of the queues actually were available. So based on that, then estimating what is the value of how many number of packets which are going to be directed to an outgoing port. Now it is a tricky business, so I have to use another variable here. I call it at the earlier slot how many slots which were free, how many head of the queues which were free, that is Fm minus 1. Out of that k packets were directed to an output port I, and since with equal probability the packets can be directed, it is 1 by n which I am taking. So that is what will be the PDF. Now what is Fm minus 1? These are total number of free slots at the end of the m minus first slot. So this should be n minus, n is total number of incoming ports minus whatever which are already occupied. So Bm minus 1 I, that is occupied slots, occupied head of the buffers at the input side for an output port I. So if I sum it over all outgoing ports, I will get, and take a difference, I will get this value. So this should be Bm minus 1 I goes from 1 to n. Okay. So this is sum of the packets which are blocked for an outgoing port I and summed over all possible outgoing ports. So whatever you remove this thing out of this, those are those many number of packets which will be coming to the front of the queue. So Fm minus 1 now is going to be written as, so let me formally write it, number of head of the input queues after m minus first slot. Okay. And these are the also queues which will have the new packets, these many number of things. So you can actually write f bar by n, that should be the utilization of the line. At any point, utilization is technically how many packets. So for any outgoing line, this should be the load. These many packets which should be going out, I need to find out what is this rho naught. Okay. So if I can find out the average value of this, then divide by n, that is a fractional utilization for n line for the whole switch. Okay, that will become rho naught. So you can, the f bar can be expressed as, let me write it here, this is a mean steady state number of free input queues free, I think, heads of input queues. So that is the f bar. So rho naught actually will be given by this. Now in limit when n actually goes to infinity, then what will happen? So steady state number of packets which are moving to the head of the free input queues and destined for output I. Okay. So that will be Ai. So that is the average value essentially. Over time this is a mean steady state value. This will become Poisson with value rho naught. Okay. So that is what the utilization which I am talking about. This is the rho naught. Okay. So once this is happening, and when in limit when I am also taking n goes to infinity, this term will now get converted to p square 2 minus 1 over p. And of course interestingly also I can actually use this expression and get Fm minus 1 by n 1 minus this summation which I am doing for n, if I know the average value steady state average of this multiplied by n should be equal to this summation. So this should be n into b bar. Okay. So, n into B I bar. So, I can write this as n into B I bar by n. So, this is what it will be. Okay. And we have already figured out that my B I bar is this value in limit when n goes to infinity, where P is nothing but technically the utilization of the line. So, that P I can replace by rho naught. So, I can write down the expression and of course, this on an average basis when I am doing averaging f bar by n, this value turned out to be rho naught. F bar by n is rho naught I have already estimated. So, this will be rho naught and 1 minus I am taking the q from here, it will be rho square by. So, now when I am making P is equal to rho naught, P is a general expression, rho naught is the value or the loading of value of P at the saturation condition. So, I am just replacing P naught by rho naught, I am looking this is the condition under saturation. So, this should be equal to rho naught. So, this will give me the value of my output utilization of the links under saturation condition, that is a maximum throughput which you can achieve in an input queued system. So, this value once we estimate, this value will be, so I can just actually use this 1 minus rho naught is equal to rho naught square to 1 minus rho naught is 2 into, so 2 rho naught square plus 2 minus 4 rho naught. So, this is what will be the expression. So, this one goes out with this. So, you have rho naught square minus 4 rho naught minus plus 2 is equal to 0. So, this will give you rho naught will be equal to 4 plus minus 16 minus 8 by 2. So, this will be now rho naught actually cannot never ever be greater than 1, rho naught is a probability. So, the second solution actually does not make sense. So, the solution of rho naught will be 2 minus root 2, this is the maximum throughput which is achievable in an input queued system, and this is roughly the value is 0.586. So, maximum utilization can go to up to which you can actually go in an input queued system is 58.6%. Okay. And remember, this is the condition when switch is of infinite size n by when n goes to infinity. So, that is the maximum which you can get. Now, the question is, can you get a throughput which is higher than this? This is what you can get under saturation. You keep on increasing your P, as I told in the graph. If you keep on increasing your P, it increases, then it limits at 0.586. It never reaches to 1. So, you are actually bombarding. So, there is no use of pumping in more and more traffic into the input queued system once you have reached to 0.586. So, roughly about 0.586 after that. Even if you try, you will not be able to go through, your queue will essentially get clogged, they will build up to infinity. Your outgoing maximum possible throughput is 0.86. So, your input has to be lower than that for a stable input queue. So, input queue will become unstable. And now, we should actually ask a question, can I do even better than this? Is it possible? Well, there is a way. Now, if you look into input queue, can I relax some condition? What I am actually currently doing is, if there is a head of the line blocking, I am just letting the packets stay, and then I am trying to ask them to go out in the next round. So, some of them are coming in. So, that actually leads to limitation of number of packets which can come to the head of the queue at every time slot, and that is 0.586, that is rho naught, and that is what lead to your limitation. So, can I do something that if they are many packets which are contending for an output, one of them will be pushed to output, let the remaining one will be dropped. So, what will be the throughput in that condition? So, let me make an estimate of that. So, in that condition, and then we will compare the situation, figure out if I can operate the switch even better. So, all blocked packets will be dropped, that is a strategy which we will take up. So, I will define, in this case every time the number of free head of the queues will be always equal to n, it will not be changing. So, which actually implies that probability that you will get in the nth time slot for an output I is equal to k. I will not be using fm minus 1, I will be using now n, because all blocked packet actually have been dropped. So, I will get nk, this is actually nck, just writing in a different way, p by n, probability that packets are coming in, they are being directed to one of the outgoing port, that is 1 by n probability. So, p by n is getting a packet at an outgoing port, k 1 minus p by n minus k. So, p is the arrival probability. We define a variable called IMI for an input, this will be 1, if output trunk I has a packet in nth time slot. Else it will be 0. So, you have to just find out what is the probability that IMI is equal to 1. So, that is a throughput of an output link. Okay. So, that is a throughput. So, this is nothing but that probability that AMI is greater than or equal to, in fact it should be greater than 0, that is good enough. So, this value will be nothing but 1 minus p by n, that is a probability that packet will not arrive, it does not arrive in any one of them, that is this probability, and 1 minus of this, at least one will be arriving or AMI will be greater than 0. So, this is the probability . Okay. So, output trunk utilization should be equal to this, so which implies that rho naught will be 1 minus p by n raised power n. And since the earlier result which we have computed is for infinite size switch when n goes to infinity, let me also take, so that I can compare what happens when n goes to infinity for this case. Okay. So, in limit when n goes to infinity, I can write this thing as 1 minus, so 1 plus minus p by n, in fact minus p by n. So, when n goes to infinity, p by n goes to 0 actually. So, I can write here minus p 1 over minus p by n. So, this can be written as limit p by n goes to 0 So, this is nothing but an expression for exponential. So, this results 1 e raised power minus p. So, rho naught has to be equal to this. So, when this value, when this loading condition for a given P, this is an outgoing throughput, this is a probability of arrival P. So, when this throughput is going to be higher than the maximum achievable 2 raised power minus root 2. So, let us find that thing out. So, 1 minus e raised power minus P. Now, you have to understand rho naught is the throughput, is the link utilization at the output side, P is the input arrival rate probability. Okay. So, if I this for this condition to be true, if you solve it, you will get root 2 minus 1 greater than e raised power minus P, e raised power plus P greater than 1 over root 2 minus 1, which is going to be P greater than natural log of 1 over root 2 minus 1, and this will turn out to be that P is greater than so this what will be the value. Now, log of root 2 plus 1 if you compute is 0.88. So, whenever your P actually crosses 0.88, if you can actually get into a condition whereby your throughput, this throughput is more than the throughput given by, which is for the saturation condition. Before this the throughput will be smaller. So, which actually, and of course, now you have to also understand P minus rho. Rho is the outgoing rate, P is the incoming rate. So, whatever is the difference, that must be the loss rate. So, these many packets per unit time per port will actually be lost at the input. So, with this actually we can understand that how the switch should be operated. So, let me now put it down. So, for n is equal, this is only for n is equal to infinity, remember. So, when your probability is P 0.586, switch actually is not operating into the saturation. It will just reach saturation, this is operating normally. After this, if your P is 0.586 but less than 0.88, your switch is actually operating in saturation. In fact, after this it is operating in saturation now, all throughout. But for this domain, dropping the head of the queues does not make sense, because we have figured out throughput will only improve when you are dropping the packets at the head of the queue, only when P will become greater than 0.88. Okay. And that is now the queue is actually unstable in this regime, because your P is more than the departure process. So, you can start dropping the packets at the input. So, you can have finite queues, you need not have infinite, because you when P is more than this, the queue will build up to infinity. So, the moment actually P crosses 0.88 in this zone, then you start accepting a practice of dropping the packets. Okay. Except one, all other contending packets will be dropped from the head of the queue. So, instead of dropping at the output of at the end of the buffer, now you start dropping from the front. So, every time new set of packets will come, you require less amount of buffer size and you operate at higher throughput performance. Of course, loss is still going to happen. Okay. So, this is how we should actually operate the switch. With this, now we do understand what is the difference between the input queue and the output queuing. Remember, what we had done is we have started with a crossbar, which is now being used as a packet switch. Now crossbar actually has a limitation, it needs a controller. Controller has to analyze all the headers, decide on the operation of the switch in every mini time slot inside the switch. This become cumbersome typically if my speed of factors are high. Okay. But if speed of factor is 1, this is what you can get at most. You start dropping and then your probability, your value or expression will be 1 over e raised power minus p. Okay. After 0.88 this will actually further improve, when will p will become equal to 1. So maximum throughput which you will get is 1 over 1 minus e, that is a maximum which you can get. Okay. This is a maximum value which you can get when p will be equal to 1. So with 0.88, when p is 0.88 you will switch over, you will move to this as the maximum throughput, which is lower than what you get for the output queuing system. Now in the next video we have to look into a scenario, because I cannot keep on using crossbars. Size is a limitation, I want to build up a higher throughput performance. So header processing time is the bottleneck. So we will now look into how the multi-stage interconnection networks actually can be used to build up a packet switching system. Of course, now one of the important thing we normally would like to have, we do not want a single processor doing the job. So we will start to build up a distributed system. Okay. So next video we will look into this. Thank you.